Let's talk about backpropagation here in this video. So this is an important topic in neural network and it's about how neural network learn. So we have input layers, hidden layers, we can have multiple hidden layers also, and then finally we'll have some output layer. So we have one output nodes here. For if we can have multiple output nodes also in output layer. And in each layer, consider this hidden layer. So each node will be a weighted combination of the previous layer. So then these are the weights. So these are the weights for the first layer. This is the weight for the second layer. So how do we write the weights? It's Wij superscript L. So Ij is basically from which node to which one? Let's say x1 to z1. This is W11 and this L superscript bracket L bracket 1, this represents, this is the weight for the first layer. So we have to find out these weights and we'll see how do we get that. So it's about, we told like it's about how do we train this neural network. So initially we start with few random weight parameters and we calculate these values, right? Any layer by layer we calculate these values and ultimately we get some y hat. So y hat is the predicted output, and also we'll have y, that will be the actual output, let's say, right? So if you compare this actual output and the predicted output, we'll get some error, right? So that will be the error. So we have to calculate gradient of that error with respect to all these weight values. So if you remember about gradient descent, so that's how we update the weight parameters is Wt plus 1 equals to Wt minus alpha, this is some learning rate, del E del Wt. So right, so these are the gradients that we calculate. So and each iteration we calculate the gradients, we update the weight parameters by this formula and we do this until we converge. The same thing we'll do in this neural networks as well. But how do I calculate the gradients in neural network, that we'll see here, because the structure you see earlier we just had a single model, right? For if you see normal linear regression or logistic regression and all, so we had only one single model, single node model. So here our structure, we have multiple nodes and this structure is complex. We have to see how do we find out the weights here. So basically neural networks can have multiple layers and thousands or even millions of parameters, this weight parameters, right? So we can have millions of weight parameters. So calculating these gradients and updating the weights is a difficult task. We'll see how do we do it here. So before going there, we'll build some intuition. So we'll see this chain rule of calculus that probably we had studied in school. So it's like consider we have a function g of f of x. So let's say we have this z is basically f of x and y is z of z. So this is the function from x to z, we have this f function, z is basically f of x and y is z of z. So let's say z is f of x, which is x square, and y is zz, which is e power z. E power z is basically what? Z is x square, so e power x square. So what is dy dz? Dy dz. Y is e power z, right? So dy dz will be e power z. What is dz dx? Z is x square, so dz dx will be 2x. Now what is dy dx? How do we calculate that? So that will be dy dx will be dy dz times dz dx, right? Dy dz times dz dx. So that's why chain wise we are calculating this derivatives, right? Calculus, it's derivatives. So this is called the chain rule of calculus. So dy dz where will be? Dy dz is e power z times 2x, e power x square 2x. So this is how we apply chain rule in scalar case. Now next we'll see for vector case. Vector case, let's say from x to z and z to y we are calculating, but here x is a m dimensional vector and these are the m values, let's say. Z is n dimensional vector, let's say these are the n values, and y is a single value, let's say. So if we have to calculate del y del xi for any xi here, del y del xi, this we have to calculate, right? So how we will calculate that? So earlier we just had one path, right? We had x to z, z to y, right? So now we have multiple paths. See, xi to z1, z1 to y, xy z2 y, xy z3y. So chain rule we have to apply in all the paths and then we have to sum that. So that's how chain rule applies in the vector case. So del y del xi will be del y del z1, del z1 del xi in this path, del y del z2 times del z2 del xi in this path, and del y del z3 del xy in this path. Is basically we are taking the summation of all the path. Z equals to 1 to n for all this path, for all, if you consider all these nodes. So del y del zz times del zz del xi. So this is how we apply chain rule for vector case. Now we'll see how do we apply this chain rule to in our case. So this is the neural network we have and we had to calculate what? Del E, del W1JL for each weights we have to calculate this. So how do we get this E first, the error first? So we are calculating this y hat. So y hat is the predicted output. Right, and also we'll have y sum actual output, and using comparing this predicted output and the actual output will get the error, right? And then we have to calculate del D del WIGL for all the weights here. So first we'll see how do we calculate the error. So we have several weight functions. We have seen lots of different types of problems, starting with linear regression, logistic regression, multi-class classifications. So consider actual output is y and predicted output is y hat, and this loss E will calculate here. So first one is mean squared error. So it's mostly used in the regression problems. So we take the averaged sum of the squared difference between this actual output and the predicted outputs. Root mean square error is basically if you just take a square root of this mean square error, we get the root mean squared error. Mean absolute error is basically if we take the averaged sum of the absolute difference between actual output and the predicted outputs. Binary cross entropy loss, this is used in binary classification or in the logistic regression we have seen. This is minus y log y hat minus 1 minus y log 1 minus y hat. So y and y hat both belongs to 0 or 1. This is binary classification, right? So this y is the actual output, this is the predicted output. Categorical cross entropy and sparse categorical cross entropy, these are used in the multi-class classification. So if you have seen my multi-class classification video, there I have discussed the softmax, the one hot encoded representation of the output. So we have k classes, let's say 1 to k, right? So the loss or error will be negative sum of all the classes yk log y hat k. For each of the classes, this is the actual output and this is the predicted output. So where yk is the one hot encoded output and yk hat is the softmax output basically. In sparse categorical cross entropy is the same basically, but we, instead of one hot encoding, we use the class indices, and this is how we represent the error, minus log of y hat. So y is basically the actual output class. So the softmax output of this actual class. So that's how we calculate here. So this is in a nutshell like how we calculate the error or loss, and after we get the error we have to calculate the gradients with respect to all the weight parameters. So quickly I will show like how do we calculate the gradients in each of the path. So let's say for simplicity I am considering this binary cross entropy loss function. So this y hat, this is the predicted output. So how do you calculate del E del y hat? So we know this is the E, right? So if we just take derivative with respect to y hat, what we will get? Minus y divided by y hat minus 1 minus y divided by 1 minus y hat, and if you take derivative of this 1 minus y hat term, you will get minus 1. And here is the same, I just reverse 1 minus y, I made it y minus 1. So this is del E del y hat. So y hat is equals to a1 2. It's both the same right here. So del E del 1 2 also will be the same. Now how we calculate del a1 2 del z1 2. What is a1 2? a1 2 is mostly considered it is sigmoid function, right? So if a1 2 is sigmoid of z1 2. So in my logistic regression video I have discussed about derivative of sigmoid function. So derivative of sigmoid function is like this. So this is sigmoid of a. If we consider calculate derivative of this, it will be sigmoid of a 1 minus sigmoid of a, right? So del a1 2 del z1 2 will be sigmoid of z1 2 1 minus sigmoid of z1 2. We calculated this as well. Now how will calculate del E del z1 2? Del E z1 2 is what? It is by using the chain rule, it will be del E del a1 2 times del a1 2 del z1 2. We calculated both here and we can just multiply this and we'll get the value. So we calculated del E del z1 2 till here. This is what we already calculated. Now we have to calculate the gradients with respect to this weights. Del E del W112, del E del W212 and del E W312. We'll see how we will calculate this. What is Z12? Z12 is a weighted combination of this previous layer nodes, right? So consider one bias also here, W012 with the weight W012. So Z12 is basically W012 plus W112A11 plus W212A21, W312A31, right? This is Z12. Now what is del Z12 del W112? W112 is only here, right? So del Z12 W112 will be A11. So what is del E del W11, right? So that will be del E del Z12 times del Z12 del W11. Del E del Z12 you already calculated here, and del Z12 W112 we just calculated here. If we just multiply this two, we'll get del E del W112. So we calculated del E del W112. Similarly, we can calculate del E del 212, del E del 312 in all this part. So that's how we apply chain rule in our case, and we calculate this gradients. So actually these gradients are calculated layer wise, and we'll see now in the next layer how we calculate the gradients. So now Z12 is what? This we already saw. Z12 is weighted combination of this A11, A21, A31 and all. Now what is we have to calculate? Next we have to calculate del E del A11, right? So with respect to this nodes we have to calculate. Del Z12 del 11, what is it? Del Z12 is what? Del Z12 del A11. A11 is already only here. So in all of these terms only here we have A11. So del Z12 del A11 is W11. What is del A11 Z11? That depends, because earlier in the output layer this A12 was is sigmoid, right? Sigmoid function. Here in the hidden layer mostly we use, or most common choice for hidden layer is ReLU as a activation function, right? So and ReLU is what? ReLU is f of x is equals to max of 0 or x. So del A11 del Z11, this will be 1 if x greater than 0, it will be 0 if x greater than 0, less than 0, and it's undefined at 0. So depends on the activation function. So based on the activation function we can calculate del A11 del Z11. We already calculate, we can calculate this. Next we have to calculate this delete with respect to all these weights. What is Z11? Is a weighted combination of this previous layer. So consider a bias here. Let's say W011. So Z11 is W011 plus W111 X1 plus W211 X2. This is Z11. So what is del Z11 W11? So this is X1. Just here we get, from here we get X1. So then what? Del E del W11, if you can just use the chain rule here, right? So del 11 is basically, you see here, used in this path. So we can just calculate the gradients in this path. What is this? Del E del Z12, from here if you see, then Z12 del A11 here, del A11 del Z11 here we calculated, and del Z11 del W11. All this we have calculated, so we can calculate this as well. So this is how gradually, like layer wise, we calculate this gradients. Now I have taken a different network here. Earlier we just had one single hidden layer, so here I have taken one extra hidden layer because I want to show two more cases here. So these are the weights for the first layer, these are the weights for the second layer, and these are the weights for the third layer. So del E del y hat we calculated here, right, from here, and this del E del y hat is used to calculate del E Z13. Del Z13 is used in both the paths, right? Because Z13 is a combination of, weighted combination of this A12 and A22 both, right? So to compute del E del A12 and del E del 222 both, we use this del E Z13, right? So this gradient basically is propagating in both the direction, and that's why we call it back propagation. So we are propagating the gradient errors in the backward direction. So this is why this is called back propagation. So now here we see del E del Z12 we calculated, and this Z12 is what? Like it's a weighted combination of A11, A21, A31. So all this is contributing for Z12. So Z12, this error will be used to calculate gradients for all these three. So this del E del Z12 will be flow in this three direction, right? Similarly, del E del Z22 will calculate here, and this will flow in this three direction, right? So now if we want to calculate del E del A11, where is A11? Here. How we'll calculate that? So A11 is used where? Z12, Z22 in both the paths, right? So if we just see the path from A11 till our output, right? So you see this is one path and this is another path, right? So we have to calculate the gradients in both the path and then we will take the summation in both. So that's what we are doing. So del E del A11 will be del E Z12 times del Z12 del A11 in this path. Del E del Z22, here we will calculate, and plus del E del Z22 times del Z22 del E11 in this path. So we'll calculate in both the path and we'll take the summation. If we just want to quickly see the calculation as well, so Z12 is what? It's a weighted combination of this three. That's this what I am just I have not taken the bias here for simplicity. Z22 also will be a weighted combination of this three. We can easily calculate del Z12 del A11, right? This two we have to calculate, right? Because del E del Z12 already is flowing from here. Del E Z22 is also flowing. We have to calculate del Z12 del A11. Del Z12 A del A11 is what? Z12 A11 is only here. So it will be W112. Similarly, del Z22 WA11. Del AZ22 del A11. A11 is here. So it will be W11122. So we got all the values and we can calculate del E del 111. So my point here was just because E11 is contributing in both the paths, so while calculating the gradients of E11, we have to consider both the path, right? And then we have to take the summation. Next, how do we update the biases? I have not talked much about the bias, so consider this note. Z13 is a weighted combination of this, right? Weighted combination of the nodes in the previous. So let's say we have this bias also here, W013, right? So how do we calculate the del E del W013? Because this weights, bias weights also we have to calculate, right? So we'll see now. So Z13 is what? It's a weighted combination of this del W013. This is the bias plus W113 A12 plus W213 A22, right? What is del E del W013? W013 is here only, right? That we have to calculate. So del E del W013 will be del E del Z13. That we will be calculating in this path using chain rule. And then we have to calculate del Z13 del W013. So del Z13 W013 will be what? 013 is only here, it doesn't have any coefficient, right? So del Z13 del W013 will be 1. So this will be 1. So del E del W013 will be del E del Z13, whatever we calculated from using chain rule in this path. So that's how we compute the gradient of the bias. And easily, as we are calculating all these gradients with respect to bias, we can use that in our gradient descent. Wt plus 1 equals to Wt minus alpha, this is the learning rate, del E del Wt for all the weights. And this is how we will be training our weight parameters.